In this brief video, we're going to take a look at a motivation for what we call matrix multiplication. Now, matrix multiplication is the general process of multiplying any two matrices that are, we'll soon see, appropriately sized, and we're going to generate a new matrix. Now, matrix vector multiplication, where perhaps we had a matrix that was maybe 2 by 2, like 1, 2, 3, 4, and a vector, let's say 5, 6, we know how this process takes place. It would be 5 times the column 1, 3, plus 6 times the column 2, 4, giving us a new vector. That was a special case where the second matrix, if you will, was an n by 1 vector, where A was m by n. So in our case, this was m and n were both 2, and this was a 2 by 1. So to motivate this, suppose we impose a transformation on a vector. That is, we impose a matrix transformation, which we know is a linear transformation, and we multiply this vector x by this matrix A, and we generate this new vector, which I'm going to refer to as y. So the idea here is that we have some vector that starts off, and we multiply it, it gets scaled, maybe rotated, and let's just say it ends up pointing there. So that's A times x, which is the vector x transformed. Now, we're going to suppose that A is m by n. Therefore, as up here, x is an n by 1 vector. Now, if in a case where A is 2 by 2, then y, which is the transformation of x, is also, notice, a 2 by 1 vector. So we start off with a 2 by 1, we get a new 2 by 1. We then apply another matrix, another transformation on this output. So then let's suppose that we take the y vector and we transform it in some way. So geometrically, what that would mean is that we would take this vector y right here, this already transformed version of x, and we transform that in some way, and we multiply it by a matrix B. Okay, so that might, again, perform a rotation, and let's just say it makes it really short, and there is our vector that we're going to call z, which is the transformation of the vector y, which is B times that vector y. Now, B is going to be a P by M matrix. Okay, so we have a number of dimensions here that I'll write off to the side. We have A, which is which we're writing as an m by n. We have B, which is P by M, and we have X, which is n by 1. Now you can see that we have really 3 different dimensions going on here. We have M, N, and P. And let's see how this all pans out. There are a couple of facts that are true. First of all, Z will be a P by 1 vector, and the product between A and B, should we choose to conduct that, will be P by N. Let's try to make sense of why this would have to be the case. So first of all, in order to get y, we take A times x. In order to get z, we take B times y. Now, since to verify fact 1, let's observe that A is m by n, x is n by 1. Now, in our case, we were dealing with 2 dimensions, but we don't have to be in 2 dimensions. We could go from 2 to 3 dimensions, and then from 3 to 5 dimensions in our 2 multiplications. So y, notice, will be an n by 1 vector by matrix vector multiplication. So then, if that should be an m right there. Now, since y is m by 1, B is P by M, well, that means that we're going to have Z, which will be the number of rows in B, and one single column, it will be P by 1. Again, from what we know about matrix vector multiplication. The size of the output vector will be the number of rows in the matrix that it is multiplying. For example, if I have 1, 2, 3, 4, 5, 6, and I multiply it by a 2 by 1 vector with the components 7, 8, to make sense of this, it will be 7 times this column, 8 times this column, and then they will be added together. Well, they're both scaling 3 by 1 vectors. It'll be 7 times 1, 3, 5, plus 8 times 2, 4, 6. And so the result that we get will have 3 components in it. It'll be a 3 by 1 vector. Now this matrix, notice, is 3 by 2. This vector is 2 by 1. We ended up with 3 by 1. Same kind of idea goes with this p by m times n by 1. We're just changing the labels of those dimensions. Now to verify fact 2, since we know that y is ax and z is by, z is, forgot my vector hats there, z is b times y, well, I can make a substitution for y. Y, I know, is equal to ax, or came from the multiplication of a and x. Therefore, by substitution, just using algebraic substitution, I have b times a times x. Okay, now I'll put this in parentheses for a moment. We're hinging on a property here which is known as the associative property of matrices. We'll learn about that soon. Here we're just trying to provide a quick motivation. So we're not going to verify this, but I'm going to make the argument that we could multiply b and a together first, and then multiply that result by x. This is what we will call the associative, just like the associative property of arithmetic. Matrices have an associative property. Matrix multiplication has the associative property as well. So see later that this is true. Now, in order for this product, which we know is still equal to z, in order for z to be the p by 1 vector we determined it should be, if x is an n by 1 vector, then that means this matrix right here, which for now, let's just think about this as when you multiply them together, you get a brand new matrix. In order for this all to work out, this would have to be a p by n matrix. That's consistent with what we're stating to be true. Now, the funny thing about matrix multiplication is it doesn't work the way we might imagine. So you might imagine taking two 2 by 2 matrices, and since we've dealt with arithmetic and you can always add matrices that are like dimensional, it must be the case for multiplication too, right? So you would think that you would just take whatever number is here and multiply it by whatever number is here, take whatever is here, multiply it by whatever is here, take whatever is here, multiply it by that, and then take whatever this is and multiply it by whatever that is. But that is not how matrix multiplication works. Matrix vector multiplication is that weird oddity that we've seen before. Matrix multiplication, the generalization of this, has that same kind of odd nuance. So we know that this matrix, whatever it ends up being, has to be p by n, so that a p by n times an n by 1 gives us a p by 1 vector. Now let's analyze b and a. We know that b times a is going to be p by n. We know by the problem statement that b is a p by m matrix. We know that a is an m by n matrix. And one similarity here that we notice between matrix multiplication and matrix vector multiplication is this inner dimension right here. So as long as those two inner dimensions are the same, the resulting matrix, its size, will be the size of the outer dimensions of what we'll refer to as the outer dimensions of those two matrices themselves. And we're going to see how this takes place in sort of a nutshell. If I do take, let's say, a 3 by 2 matrix. So that's 3 by 2, which means that the dimension of this matrix has to be 2 by something. Let's make it a 2 by 2. We'll just put 7, 8, 9, 10. The way this is going to work, to give you some intuition, is we're going to think about this matrix as having 2 columns, which it does, right? It has the 7, 9, and then the 8, 10 matrix. So the only difference between matrix vector multiplication and matrix multiplication is that we're going to end up with 2 columns instead of 1. The first column that we get will be, again, the matrix vector product, but now it'll be between 7, 1, 3, 5, 9, and 2, 4, 6, and those 3 components will end up going here. Now, we're going to do one more matrix vector multiplication to get our next column, namely 8 times 1, 3, 5, plus 10 times 2, 4, 6. We'll get 3 new components, and those will form the components of that second column, thereby giving us 3 rows by 2 columns. So it's more involved in the sense that there's more arithmetic to be done, but it's exactly just a multiple iterations or multiple matrix vector multiplications that will take place. How many matrix vector multiplications? As many columns as there are in this first matrix. And because these components are all scaling 3 by 1 vectors, notice that the 3 rows that we end up with here are the 3 rows that we started with in our first matrix. We'll see how this works in the next video.